about SoC design methodology. And in order to present, we have two senior colleagues of mine, Amol Agrawal and Gaurav Jain. Both Amol and Gaurav have more than a decade of experience with NXP. And I welcome Amol and Gaurav on this forum. Welcome Amol and Gaurav, and I think you can start now.
Good evening, all. Many thanks for your collaboration with NIT Tiruchi. Myself, Dr. Srinivas Luchogi, and along with our HOD sir, Professor M. Bhaskar sir, and another colleague, Dr. B. Naresh Kumar Reddy. So, we are very happy to be part of this live webinar. I request our HOD sir, Professor M. Bhaskar sir, to deliver opening remarks regarding this webinar. Over to you, sir.
Yeah, good evening, one and all. First, I appreciate the initiatives taken by Srinivas Jogi and Naresh Kumar Reddy for this webinar. And from NIT and from Department of ECE, I thank NXP Semiconductor team making this wonderful opportunity to the students of NIT. So I welcome Mr. Akhil Jain, Gaurav Jain, and Amal Agarwal. Sir, it's a really wonderful opportunity to our students to know about the complete SoC design flow. So a warm welcome and thanks for this opportunity. I would like to share some slides about our department. Can I share it?
Yes, sir.
Yeah, sure. Yeah, sure.
Yeah, are you able to see the screen?
Yes, sir. Yes, sir.
Okay, thank you. See, the Department of EC NIT Trichy is one of the oldest department. It was started in 1967 with 40 Cs, but currently we have 145 students BTech 4-year program. And we have two MTech courses. One is Communication Systems, another one is VLI System. And both the courses started quite early, and even we are proud to say that we are the first institute to start an MTech program in VLSI system design in the country. And all our programs are accredited with a maximum of 6 years. And currently we have a very good faculty strength. There are 29 faculty strength. And all these faculty members are working in different areas of research, starting from signal processing, microwaves, VLSI, analog, digital, embedded, IoT, AI, ML. So we have a very good research group in different domains of pioneer research areas. And the last 5 years publications, so totally we have 664 publications, out of which 432. And even we are proud to say that we have more number of journals published in Q1. And our faculty has authored 16 textbooks and 53 book chapters in the last 5 years. And these are the textbooks which are being authored. And last 5 years, the consultancy project is around 8 crore we are able to get from funding agencies. And total number of PhDs completed is 114. The last 5 years, we had a maximum PhD awarded. 60 and almost 70 students admitted, and MS research. And it is interesting, or it is important to convey to NXP also, the student or your employees, if they really would like to pursue their MS and PhD in NIT Trichy, most welcome. For example, one student from SanDisk and one student from ST Microelectronics. They have joined for part-time PhD and they have completed their PhD and MS also. The advantage is they are supposed to come and stay just 6 months for completing their coursework. After that, they can continue the research in the institution or the industry where they are working. So this is a rare opportunity for the employees of the various companies. They can graduate with masters and PhD. So already this model is working out, and more company employees from Bangalore, Chennai, they have registered for MS and PhD. And this admission will happen every 6 months, January and June. So they can apply and they can have their qualification to the maximum. And we have 12 curriculum laboratories, and there are 18 research laboratories. I told you, each and every group in our department, they are associated with one of the research lab. And this is a very important facility. Recently, it is being created. It is called Center for Electronic System Design and Testing. We have a RF probe station, we have a parametric analyzer, we have RF source up to 6G and VNA up to 6G, and we have an automated antenna measurement setup. So this is a complete lab where you can do all the device testing, your die. So all kinds of testing we can do here. So our students are using this facility. And this is a new one. This is Center for SoC Design and Fabrication. The complete center is being sponsored by one of the alumni, Raj Shanmugaraj. A single person has given 1.9 crore in 2022. And some research work related to SoC is going on with SEL Foundries. So my request is probably you can NXP can join with this group, and if you want to do some research projects, probably you can give that this group will work on the SoC design, and they'll be able to have a joint research thing which can be done in this lab. So the complete funding will be done by this lab. So coming to the placements, NIT is having a good track record of placement. So this is the UG placement. So 2023, we have almost 97% of the students get placed. And also, if you see the number of companies which are visiting, it's increasing exponentially, or maybe it's increasing rapidly. And another thing, most of our students also have an aspiration to do their masters and PhD in foreign universities, and after that they are coming back. So that's all about on the department side. So once again, I would like to reiterate that NIT Trichy is offering more avenues for the people who are in industry to come here and pursue their degrees, or if you want to have joint projects, collaborative projects, we have a large number of research groups. So you can definitely have joint hands to reach better heights. Thank you. Thanks for the opportunity.
Thank you, sir. Over to you, Mr. Vasimai. Over to you.
Yeah, hello. So thank you so much for this excellent overview, and it's great to see the research which is going in your college, and it's always good to have a collaboration between industry and academia to devise the new ideas. So yeah, so for sure, NXP would like to partner with the NIT Trichy in future. So we can now start with the topic, right? Yes. Okay. So today's topic is the overall overview of SoC design flow. Okay. So before going into details of the SoC design overflow, let's see how the overall semiconductor ecosystem work. So from the design to the end product. So on the left hand side, you can see the semiconductor design company like NXP, which works on the tools provided by the EDA vendors. So and which helps us to design the chips. And then in the middle, you will find the tier 1 suppliers like Bosch, Conti of the world, who will use these chips to develop the system use case. And then ultimately, once that overall system is available, which will go into the end product, which would be developed by the automotive OEMs. So this is how the overall ecosystem works. So we will not go into detail of this. Our more focus is on the semiconductor design flow, but this is just to give the overview to everyone that how we start from the chip design and how the end products go to an end product. Okay, so as we say, the design company's main focus is on the chip designing, and this is how the overall ecosystem works. So you start from a foundry like TSMC, Global Foundry, which gives you the process design kit. So process design kit, we will go into detail of that. Process design kit is like a set of rules which help us to develop chip. And then these are the multiple segments of a chip design, which can involve the custom design, like your standard cells, your analog macros like PLL. Then you have a semi-custom design, which is basically the bread and butter of any typical SoC, that you would have the architecture specs. Using architecture specs, you will develop RTL, and then you will synthesize that logic, and ultimately it will convert into a logic gates, and then you will do all your sign-offs. And then you also need to, once your silicon is out, then you package your design, you do all your silicon validation and qualification, and these rules are also governed by the foundry, and that's how the end product, the final chip is ready. Okay, so before going into deep down into SoC design, just see how the overall semiconductor industry is growing. So semiconductor industry still is not too old. It's still 60, 70 years old, and it's still relatively young compared to other conventional engineering fields like civil engineering. So in y-axis you see the number of units which are getting shipped by the overall product companies, and on the x-axis you see the span. So you can see that how the industry has grown over the year, and you can almost see exponential growth. And in every decade or there is an era. So we started from the mainframes to mini computers, to PCs, to cell phones in the new millennium, and now we all know the buzzword artificial intelligence and IoT. This is the era of the artificial intelligence and IoT, and you can see the number of units getting shipped. So for sure, the way the semiconductor industry is growing, there is a lot of growth and opportunity here to do innovation and generate the cutting edge products. So now we will go back to the topic, and we see what are the opportunities for the skill development in the semiconductor design. So we will see what are the different skills which are required for the different fields of the chip designing. So process design kit, as we touched earlier. So it basically bridges the technology world to the design world. You can assume a process design kit as a set of rules for a given technology. So your process design kits would have your SPICE models, the rules for the parasitic extractions, rules for the manufacturing, how much should be the spacing between two nets, what is the pitch, what is your technology node. You often would have heard the terms like 5 nanometers, 16 nanometers. So for every tech node, there is a process design kit, and these are the on basis of these rules, you develop your devices. So the skills needed, if someone want to excel in this field, the skills needed are the device engineering, because it is mostly you deal at the transistor level, CMOS design. Of course, you require the EDA tools to build the basic building blocks. So these are the skills which are required if someone want to do a research and in this area. Okay, so once you have this process design kit available, you build the building block. So the building blocks are like your standard cells, like inverters, buffers, NANDs, or your building blocks could be memories, IOs, and analog macros. So using those set of tools which are governed by process design kit, you develop this cell. So this is more like a custom design. And we called it the world of transistors. So here again, the skills which are required are CMOS basics, circuit design, because now circuit design will come into picture. You need to do a layout design, and then you need to do simulations and extractions. So these are the skills which are required if someone want to excel in the field of the custom design. So next is the semi-custom design, or we say it's a word of IP and chip design. So which is where most of the design companies, where you hear like Intel, Nvidia's, I mean all the companies, and NXP is also in the one of the pioneer of this. So where you start with the RTL design, you got your architecture specs, you convert your architecture specs into RTL design, you do the RTL and gate level simulations to verify the functionality. Then you convert that into the logic gates, and this process is synthesis. And by the way, we will go one level deep into this, but this is just an overview that how the overall things work. That you will start from the RTL design and you go to synthesis. Once you have done converted into logic gates, then you will do floor planning, you will do place and route, and finally you will do all your timing sign-offs and the design rule sign-offs. And then you will achieve your tape out, and then it would be sent to the foundry. And the skills needed here are the digital design basics. So you need to have an sound knowledge of the digital design flow knowledge, that how the overall flow works. And EDA tools knowledge is also required if someone want to excel in this field. So once your silicon is available, next is you need to basically package it. So packaging is the next step. That your silicon is available, then you do a packaging. So here you have heard of the multiple package type. It's a flip chip or wire bond, or it's a Bezier package. Or it's a silicon in package. So after your silicon is out, you do a packaging. And here skills needed are the substrate design, package know-how, overall silicon in package specific skills are required in this field. So once your silicon is available, you have packaged it. You also need to do a test that whatever you have simulated using your tools is actually working or not. So in a summary, if this was your silicon, you will apply a known stimulus, and then you expect a known response against this stimulus, and you will verify whether this is working or not. So there are different fields of the engineering, whether you want to validate the functionality, or you want to check the connectivity. So here the test engineering come into picture, and here his skills required are the hardware-based test on the silicon. So now I will hand over to Gaurav, my colleague, who would cover the front-end design flow, and then I will take it back to cover the back-end design flow. Over to you, Gaurav.
Thank you, Amol. Thank you for covering the most part of the SoC design overall. So let me continue with the design methodology. So can you please pass over the control? Okay, so I'll start with the design methodologies. So basically to enable the SoC design, so what all methodologies are needed. So we'll not go into details, but how that plays a crucial role, right? So if you just look at today's architecture, so we are taking example of automotive here. So the today's architecture is a distributed flat architecture, where we have a single MCU for each particular application. That's why you see here multiple orange dots that basically represents one MCU for each application. And there are kgs of wires. So if I say kgs, right, which travels from front to back or back to front in our car. And going forward in tomorrow's architecture on the right side, you see it's a domain architecture, where multiple MCUs, they will be part of the single chip, which will be basically high performance domain MPUs, which will be controlling multiple applications. So if you just have a look at the top of this picture here, the connectivity wise, right? So most of the connectivity infrastructure will be controlled by a couple of MPUs instead of hundreds of MCUs. So that's how the architecture is being revolutionized from hundreds of MCUs to a couple of MPUs on board here. Okay. Yeah. So basically the design flows, so they must address the overall solution here. So the opportunity here is to maximize the system level architecture leverage, and the benefit will be the optimal device architecture for a given set of features, basically, which will eventually lead to the optimal PPA. So PPA stands here the power, performance, and the area targets. So as we are moving ahead in this domain-based architectures, so software plays a crucial role along with hardware, where the customers are looking forward to test their software to make sure that the hardware that they are going to test, that they are going to get, whether that behaves as they are looking forward. So that's why we need to enable customers with virtual prototypes. Basically, it's a prototype of the hardware that will be eventually on the silicon, so that customer can play with it. They can use it to develop the software. The system level modeling, that is also another aspect using which, right, so the performance and the other things that can be tested on that system level modeling thing without the actual hardware in place. So that's how enabling the customers with the virtual prototypes and the system level modeling. So we need to make sure that the specification that we are going to build on silicon, so those are meeting the customer expectation. Okay, so functional safety, so safety and security. So these are two important things. So when we talk about the automotive SoCs, there are standards about the functional safety, the ISO 26262. So no chip, right? So that can get into a car without getting the certification about this functional safety on this standard. So if you see on the picture here, so it started with the fail-safe, right, where we just need to detect the failures, and going forward it went to the fail silent, where the reaction. So we also need to react to the failures to bring the chip into the either fail-safe operation, or basically to reconfigure the part of SoC, where basically either we can reboot that particular part, or we can basically go into the safe mode operation. And going forward, it will be about the prediction of the failures, right? If there is a failure that will be coming into picture, the kind of latent failure, so there will be a prediction kind of thing also that will be coming into this. So on the right side here, how do we calculate the risk? So they are ASIL standards. So ASIL A to D. So D being the highest in the safety, and A being the lowest here. So risk is equal to severity multiplied by exposure and controllability. So basically, if the severity is high, in this table here, you see S1, S2, and S3. S3 being the most severe severity. And then if there is an exposure which is quite high exposure, you can basically assume it as the likelihood of getting the failure in the design. So that is equivalent to exposure here. And the controllability is basically how well you are able to control that failure in the design. So if like all these three things are very high, the severity, exposure, and control, that's where you need most instrumentation in the design to check that, right? So that's why those particular portion of the design must be ASIL D compliant, which is basically the highest safely compliant. And similarly, it would be ASIL A or ASIL B, depending upon the particular application or the particular area of the design where those are needed. So so all these topics are very vast in nature. So we are just trying to give you a very high level overview that what all needs to be considered in SoC design apart from the standard function that we have, right? So safety is one of the important function thereof. So going to next slide, which talks about functional the security in the automotive architectures. Yeah. So if you see on the rows, so we have secure interfaces, the gateways, the secure network, and the secure processing. And on the column side, if you see prevent access, so we need to we basically try to build device, right, which can prevent the access, the unauthorized access into the SoC. So assuming a car, the autonomous car, right, which is basically running, so no one should be able to hack that MCO, MPO on that particular car, right? Otherwise, it will be not only unsecure, it will also be unsafe, right, for the passengers or sitting in that car. So M2M authentication and firewall. So that is just one mechanism. So where it's a machine-to-machine authentication is there to make sure that there is no unwanted access to that particular MCO, MPU. And similarly, we have secure messaging and code and data authentication at startup. So whenever the chip boots up, so the authentication takes place of the code which is going to run as part of application, whether that is a secured code, whether that is authenticated code. So all those steps are run at the startup of car. And going to the second thing here, the detection of attacks. So if there is any attack, right, by any means, assuming there are some security vulnerability, and there is if detection attack happens, we should be able to detect that attack, that it is not a authorized code or application. So this IDS, the intrusion detection system, so it is not just someone breaking into a car, it is someone breaking into the MCUs, into the software of that particular system, right? And similar to the authentication of code at startup, so they are runtime authentication also. So at regular intervals, it keeps on authenticating if there is any unwanted access that has happened in that software. So those kind of mechanisms are put to basically detect the attacks, runtime attacks. And then if there is attack happens, then we need to make sure that the impact should be as minimal as possible. So there are instrumentation for that also. The separated functional domains. So basically that SoC is divided into multiple domains, so that if a attack is detected in particular area of the design, so that only that particular area of the design should be rebooted, and all other design should kept functional, and we should be able to basically boot that particular area. So that is just one example here, how basically we can reduce the impact of the attacks. And then finally, the fixing of the vulnerabilities. So once the vulnerabilities are detected, so those are fixed via the OTA updates. So in your mobile phones, you must be getting the OTA updates, right? And most of them, generally, those are security updates to fix such vulnerability that I'm talking about here. Okay, so moving to next slide. Yeah, so let's get into the actual SoC design here. So this is a high-level overview of the basic IC or SoC design, starting with freezing the product requirement. So we'll go into each topic here, each box that you see. Going to next slide, Amol. Yeah, so let's start with what is SoC, right? So there are different views about SoCs. So some people say that the VLSI manufacturing technology, right? So that has advanced so much that we have managed to put millions or billions of transistors on a single die, and it enables designers to put system on chip that moves everything from board to chip eventually. And then there are views, there are set of people which say that SoC is a high performance microprocessor, since we can program and give instruction to microprocessor to do whatever we want, right? And then there are other set of people where they say SoC is the effort to integrate heterogeneous or the different type of silicon IPs on the same chip, like memories or microprocessors and the various logic in design, and including the analog circuitry. But is that true? Yes. So all these statements are partially correct, but not really accurate. So going to next slide, Amol. So what is basically SoC here, right? So SoC is more on the system side. So it is the chip, the software, and also the integration part of it, right? And what is chip here? So it includes embedded processors, the ASIC logic, and the analog models or the analog circuits, and also the embedded memories, the on-chip RAMs or the ROMs that you see. The software is basically where we have the code which eventually run on the application as part of the SoC. Yeah. So it comes with the compilers, the operating systems, simulator firmware, where the clients or the customers, they can use that particular environment to develop their own software, the development environment, and also along with some part of the software that we provide along with the SoCs here. Then finally, the integration. Integration is about including the SoC and the software that we are providing in the whole system solution, because it is not just one MPU that will be on the board. There will be multiple MPUs, right? And they might be coming from the different vendors, chip vendors here, where NXP is one of the vendor. And it also includes the consultation to the vendor to basically get it working in the whole ecosystem, along with the technical support to make it work. So that's how it's a complete SoC solution here. Okay, so now going into the high level introduction. So this is the end application. One of the end application, the car, where you have electronic system, right? So it basically will be having a motherboard, and on the motherboard there will be multiple MPUs that we talked about. And if you just zoom in one particular MPU here, one particular SoC here, so it will be basically having multiple modules or the IPs that we'll talk about. And it will further be having gates at the end. These gates, they use a CMOS inverter, that is a basic building block. And if you further zoom in, it will be the device side that you have the source, drain, gates. I think this is what you must be studying in your colleges. Okay, so going to next slide. Let's talk about now how the complete SoC design starts. Starting with the product requirements. Basically, the system engineers, they go in market, they meet customers, they try to understand the requirements from the customers, and basically they negotiate with the customers depending on our portfolio that we have available as an architecture. Then depending on that, they negotiate with them and come up with a proposal. Those are called as a market requirement documentation. So that terminology could be a little bit different in different companies, but I'm just referring here at high level that's how the market product requirements are captured. And then that they will be further basically mapped to company specific portfolio, like here the NXP specific architectures, where it will be provided to the architecture team for the further deep down. Okay, so from the product requirements, so it will get translated to the architecture definition. So the architecture definition will be basically next level documentation, which are more close to the RTL, while the product requirement is more close to the market or the customer specification. And from the architecture specification, we have the detailed design technical specification, basically, which also captures like what kind of modules we need, what kind of connections, or what kind of performance. So all those will be there in the detailed design technical specifications. So as part of architecture specification, so we get this kind of block diagram where it is captured, right? So just giving example, so in market, assuming the system engineer is coming up with that we need so and so performance from the microprocessor. Then depending upon the options available, so that architecture team and system team, they work together to come up with a particular microprocessor that should be there on this particular chip to meet the customer requirement. And similarly, all the other IPs that you see here, so they basically will relate to one or another customer requirement. So that's how this top level block diagram is put together by architecture team. So that's one of the starting point to start designing the SoC. Okay, so now coming to the chip RTL model. So once we have the architecture specification available, so we start building the model. So in chip level, in the RTL level chip model, so IP is one of the building blocks. So they are reusable IPs, which we basically reuse across SoC. Like if we talk about the UART or LinFlex, right? So those are very standard IPs, and those are available on the shelf. We just need to pick them and plug it with the required parameters in the given SoC. So IP comes with the various views, the stub view, RTL view. Just on the right side of the picture, you can see right stub view is just the pin list without any actual code, so that the RTL integration can move forward, right, without the actual code if it is kind of a new IP which is still being developed, right? So that is how the IP basically IP stub view enable the RTL integration without the actual code in place. Then there are other collateral also which comes as part of IP. So when I talk about IP here, it mostly it is in-house IP, but there are third-party IPs also which basically deliver all these standard collateral here. So once we have identified all the IPs that need to be there on the SoC, right? So the SoC we start plugging in all the IPs with the correct parameterization, with the connections as defined in the architecture specification. So the SoC chip model, basically it also includes the interface and the IO interface, which will eventually be talking to the other SoCs on the board, right? And it defines the chip connectivity, the overall chip connectivity from module to module. Yeah, so once the chip, the RTL level model is available, so we need to make sure, right, that that it is verified, so that once it gets onto the silicon, right, it should behave as it is expected. It is should be meeting the intent of the design, and also should basically meet the specification that customer put upfront. So verification, again, it's a vast topic. So just trying to capture a couple of slides here. So the fundamental activities that that are performed as part of the verification. So verification engineer is responsible to generate the stimulus. So stimulus is basically the test case. So stimulus is basically the test case.
તો એવું જ છે તમારો એક જે સબ્જેક્ટ છે એક કમ્પલસરી માઇનર સબ્જેક્ટ જે ઇલેક્ટ્રિક લેવાનો છે માઇનર.
Okay, someone muted me also. Okay, I hope I am still audible. Okay, so verification engineer is responsible. Verification engineer is responsible to generate the stimulus, which basically excites the design, and also responsible to put the monitors and scoreboard in place to check the correctness of the design response. And at the end, the quality of the verification is measured, right? So there are multiple techniques, right? So the coverage, the code coverage, toggle coverage at the SoC level, which are basically monitored to sign off the verification. So if you look at the bigger picture of the verification, so we get IPs, we get architecture specification, the pin muxing, and SoC logic. So SoC logic is basically which is not a standard IP, but it is needed to integrate multiple IPs together. So it is also called the SoC glue. So by bringing all this stuff together, so the SoC netlist, this is still RTL level netlist that is prepared, and then there is a verification environment around this netlist where we have clock, reset, or the pin drivers to basically drive the interfaces at the SoC level. Then there will be monitors, checkers, scoreboards, and definitely the BFMs also. Those are the bus functional modules to drive something specific within the SoC. So that's a high level overview of the verification. So jumping to next thing here, that is the DFT. DFT is designed for testability. Okay, so So why it is important to test the chip, right? So once the chip come out of fab, right? So we need to make sure that there are no stuck at fault at least, right? And chip is usable. So what is testability? So the attributes, the design attributes that measures how easy it is to create a program to comprehensively test the manufacturer design quality. And the design is testable if we have all the internal nodes of the interest. If we can control them, if we can observe the interested nodes at the chip, at the output of the chip, right? So then it is called the design is testable. And overall, when we talk about DFT, it is the methodologies, collection of methodologies, right, which results in the creation of a testable design. So just an example here about the controllability and observability as part of DFT. So if you see a node here, which is basically marked as close at A. So if there is a fault at A, and the orange box, assuming it is a AND gate here, and if B input, right, so if it is 0, so the fault will never propagate to the output Z, because the AND gate will always be 0 if one of its input is 0, right? So that's where we are saying that we should be able to control the B pin, right? We should be able to bring the B pin at 1, so that the fault at A should be propagated to Z, and Z should be able to come at one of the chip output, so that it is observable, right, once the silicon comes. So once the silicon comes, there is no way to peek inside the silicon. Only way is we can basically shift in or shift out at the chip boundary. So that's where we are saying the flops or the nodes, they should be observable. Okay, so if you see here on the right side, so before scan insertion, so we have a D flop here. So once the scan is inserted, basically there is a multiplexer which gets seated at the D input. So one of the input at the multiplexer 0 input, right? It's a functional data, and on the 1 it is a scan data. And the scan enable, so that is controlled by the DFT vectors. So basically, by this technique, so we are able to control the inputs of any flop, right? And if you see on the below picture here, so whenever the scan enable is high, so the data that is coming on the scan data, that will be basically propagated to output. And in between, so the when scan enable is low, so we capture the actual functional data that is being captured by the flop to make sure that the flop is actually functional when the silicon comes. So why DFT is important? So there could be manufacturing issues once the silicon is there on the die. There could be contamination that cause metal bridges to not behave properly. There could be defects in the silicon bridges, which may lead to some nodes in the design either stuck at 0 or stuck at 1. It could be because of the photolithographic defects or the other basically silicon manufacturing techniques. There could be actual manufacturing issues which we should be able to identify by the DFT techniques on the ATE. So what is the result of the manufacturing failure? So it could lead to a part to become non-usable at all, right? Where basically we need to throw that part away. And the second implication could be the part cannot work at the spec frequency or at the full frequency. So we may need to sell that part at the slower speed, right? So the techniques mentioned here on the DFT side, the scan, as we just discussed, right? The scanning where we can control the flops in the design. Then there is a memory based. Basically, it's a built-in self-test of memory. So those are the memory hard macros that we need to test, and there is a built-in self-test in the memories using which we make sure that memories are testable on the silicon and they are working. Yeah, JTAG is basically for the boundary scan, or the JTAG is basically the main thing using which we interact with the design, the JTAG interface. Also, it's a standard interface available. Yeah, so how this DFT fit in the flow? So once we have the specification and the RTL code available, so that gets synthesized, and we have the scan insertion on that netlist. On the scan inserted netlist, the ATPG, so that's a standard tool available from EDA vendors, automatic test pattern generator, using which the patterns are generated, and those patterns are verified on the RTL level or on the simulation to make sure that those are working fine, and we are able to get the coverage that is basically claimed for that particular SoC. And the same vectors also get handed over to the test engineer, so that once the silicon comes, those vectors should also get passed on the silicon to make sure that silicon is functional enough. Okay, so Amol, I'll hand over back to you to cover the physical design part.
Yeah, thank you, Gaurav. Thank you so much for covering the front-end part. So we will now cover the physical design flow, that what happens once your RTL is available and how you do tape out and your silicon comes. So as Gaurav covered the part that how we freeze the means from the product requirements, how we generate the RTL, we verify that. And the next step is that how, because RTL is still your code, right? So now you need to convert into technology specific gates. So this is how your physical design and those things come into picture. So let's start with the physical design flow. So physical design flow itself in itself is a basically sum of multiple steps. So you would first have your chip top netlist. You convert your RTL into logic gates, and then on that netlist you do the floor planning. Then you do the physical synthesis. So physical synthesis means that all your net delays and those things will come into picture. And then you will do routing. Routing is the routing as per the technology specification, that how many metal layers are there, which net will go into which metal layer, what would be the spacing between those nets. That thing will come into picture. Then you do a parasitic extraction. Parasitic extraction is basically now calculating the RC value of those nets, because those nets would not be ideal net. It will when it would be connected from one gate to other gate, there would be some delay associated with that. And to know that delay, you need to know the RNC value, resistance and capacitance value, and then you do your SI checks. SI checks is basically your signal integrity checks, that if those nets are coupling to each other or not. You do a static timing analysis whether you are meeting the spec or not. Spec is, say, target is that this processor need to run at 1 gig. So whether the logic between two register stages we are able to meet 1 gig or not. So all those, basically the design timing intent would be covered through static timing analysis. And then you also have the physical checks, you that whether say any spacing between nets is not meeting the technology specification or not. So that would be covered in your physical checks. There are, say, no short, two nets are not overlapping to each other. So all this would be covered in the physical checks. And then ultimately you would have tape out and it would be shipped to foundry for fabrication. So now again, we will see what is a floor planning. So floor planning, you would have, as we discussed in the earlier part, that you would have two sort of things. One is your full custom design where you have, say, analog memories, analog PLLs memories. So this would be like your hard macros, which you would fit into your floor plan. So suppose there is a square floor plan. This is very ideal floor plan. It doesn't need to be a square floor plan always. A chip would be a square or rectangle in nature, but within chip you could have the multiple blocks, and those floor plan could be rectilinear also. But here, for simplicity, let's assume you have one square floor plan and you will fit your macros. So different first you will fit your different macros, and then so this is now assume like your a chip where this blue block is a sub block in it. So overall, this square is a chip, but within that you have this sub blocks which you called as subsystems, or you can also call as hard macros. And within each hard macro, you will have the further subcomponents, be memories or analog PLL or your digital logic. So now suppose we do a floor planning of one sub block. So here again, you would have few memories, few analog macros, but then you also have the sea of gates. So this red is like a sea of gates, which is the RTL. You have the RTL, you synthesize it, and then you place it. So all those logic gates are depicted here by red color. But then along with that, you would have the other hard macros, which are coming. It's this hard macro also would have some logic gates, or it may be some different logic gate, but it's suppose it is coming as for you a hardened IP. So say this is suppose developed by NXP, but this hard IP or memory could be coming from some other memory vendor. Say it could be coming from ARM or TSMC, from anyone. But so this is like a hardened IP. You are not synthesizing this logic on your own, but you are using the complete placed netlist or placed GDS for this portion of the logic. Okay. So what does basically physical synthesis does? So physical synthesis is not only converting your RTL into a logic gate. So the goal of synthesis is that you achieve the optimal PPA. So what is PPA? PPA is power. So synthesis will govern that what type of logic gates you are using. So you can't have the luxury to use all the fastest gate. So this would be a trade-off between power, performance, and area. So the penalty of using fast gates is that you would burn more power, but if you would use slow gates, then you might impact on the performance. Similarly, there could be area overhead, whether you need a logic gate of, say, higher drive distance, how much distance that logic gate can drive. So overall, your physical synthesis will require that you trade off between these three things: power, performance, and area, and you try to find a balance where all three specs of the design are satisfied. You can't, so if suppose your die size becomes very big, then your product may not be competitive in the market. If your power goes beyond a budget, your product again may not be competitive. But and at the same time, if suppose your processor is running at very slow frequency, again your product would not be very competitive. So you need to find a balance that for to meet your power performance and the die size target, you iterate between this, and this is done in a logical synthesis step. So this is the first step. It's not that this is done and dusted at the synthesis stage, but synthesis is the first step where you iterate between these three major KPIs. Okay, so next is your standard cell placement. So as we discussed, you would have floor plan. So in floor plan, you would have this rails. So this rails, if you look at any typical floor plan, you would see the alternate the VDD and VSS rails. So this is a red color is your VDD rail. Then in blue color, you have your VSS power rails, and between this VDD and VSS power rails, you will place your standard cells. So this standard cells are coming again as a part of package for you. I mean, you are not developing this standard cell. So this AND gate or OR gates are coming from a library vendor. So it could be again a library coming from TSMC, or you could develop an inbuilt library also. But it's not that this library you are developing on its own for a chip. This is coming as a pre-hardened library gate. But yes, compared to memory, it would be smaller in shape, and you would place it between the rails. Okay, so once you are done a placement, you need to do a point-to-point connection between, say, two gates. Your two gates need to be connected through metal routes, and we typically use a Manhattan routing. So your nets would either be routed in the horizontal direction or vertical direction. So you have a metal stack. So it could be a 13 metal stack, 15 metal stack. So what a 13 or 15 metal stack means, that you would have the set for 13 metal stack means you have a 13 metal layers to do a connections. So why you need too many metal layers? So since now we are developing a chip that has the, say, billion transistors on a single chip, so this needs a lot of routing. So this routing, all this routing can't be done on a single metal layer. So you require multiple metal layers, and it's not that a net will only be a single net. Suppose there is a connection from one AND gate to another AND gate. So that doesn't mean that that net would be routed on a single layer. It can suppose this is your M3 layer, and now it need to go into other layer. So to connect into M4 layer, you will have via a metal via, and then you will go into the other layer, and then it would be routed in the other layer. So once you have done the routing, so as we discussed earlier, your nets are not the ideal. So ultimately, these are the nets, metal nets, which would have some RCs. So those RCs those RCs would govern the delay. So here it's showing, suppose this is your metal piece. This is the width of the net, this is the length, and this is, say, your overall thickness of this net. So overall, this width and thickness and the how much distance you are spanning from one point to other point will govern the delay of this net. So this is the physics that we have studied in the school time also, that your overall resistance would vary with overall your width and the thickness of this net, and then how much long is your net, that will determine your overall the resistance. And then your C capacitance is it is dependent on the overall height. So this is your ground cap, that how much from ground your net is there. Then it is also dependent on how much wide is the overall metal piece. The more the overlap between two nets, the more would be your capacitance. And then the dielectric is we know is the property that what is the dielectric coefficient that will decide that what would be the overall capacitance between these two metal pieces. And then you have the coupling cap. So one would be the inherent cap of this metal piece, and then would be the coupling cap. This coupling cap would be dependent what is the spacing between these two metal pieces. Okay, so this is obvious that your both coupling cap and the substrate cap would vary with your inter and intra-layer dielectric constant. So one dielectric constant is this, then second is the property of this metal. What is the dielectric constant of this metal piece? Okay. So another very interesting thing is the STA, and I believe many of you would have solved those setup and hold timing puzzles. So static timing analysis, as we touched up briefly earlier, is that how you are meeting your performance spec. So when you say that a circuit is need to work on a 1 gigahertz, so this means that you need to verify that whether that circuit is working on 1 gigahertz or not, whether you are overshooting your budget or you are within your budget. So this all that analysis is covered as a part of your static timing analysis. So static timing analysis has multiple things. One is your internal register to register timing. So suppose this is your design netlist. So there could be an internal register to register logic part, and then there could also be the IOs, because ultimately you would be feeding some inputs to this chip and you would be getting some outputs. So you would have some timing specs that you are giving these inputs and whether your outputs are coming at the desired speed or not. So how the overall the delays are dependent. So there are multiple things. One is your delays are dependent on your technology rules and circuit library, whether it's a 5 nanometer node or 16 nanometer node. As you lower down the tech node, you will find the faster cells. So all these things will decide that what is the delay of per unit cell, this technology rules. Then how many logic gates are there overall? It will decide the overall delay of that logic, and ultimately you will do a setup and hold timing analysis to see if your design is meeting your desired spec or not. So okay, so once you are now done with your timing analysis, next is your physical checks, because ultimately you need to meet the technology specifications, that how closely you can route two nets. It's not possible that you do a short between two nets, right? So a technology constraints whether how close your those two nets can be routed, what should be the minimum spacing, what is the pitch of that net. So all these things are covered in your DRC. So for a particular technology node, FAB creates and provides set of design rules, which we call as DRC tech or DRM also. So these rules dictate how each layer should be drawn in your CAD tool. So for example, if you have a C90 tech node, your metal 2 must be at least 0.14 micron wide. Similarly, it also decides the overall, if you have overlap between layers, how wide your VR should be, what is your VR definition. So all these things are covered in your physical check. So you have routed your netlist, but whether that routed netlist is meeting all those rules or not, this is covered in the physical check. Then you have another physical check, which is LVS. So LVS is your layout versus schematic. So you have two things, right? One, you have layout. Layout is say your metal connections and those things, and then you have a schematic. Ultimately, it would be your PMOS and NMOS connections connected through your some schematic. So ultimately, your layout and schematic should match. So this is where we do a LVS thing. So it defines rule how to drive your device and interconnect nodes. It rules also, so it's attached name to the extracted nodes, and then extracted circuit is compared against the reference source. So reference source is your layout, and this is your extracted. This is your spice net list. Okay, so once now you have done your timing analysis, you have done your physical checks, you are ready to ship your chip to foundry, you are ready to do a tape out. And once a tape out is done, you do the validation. So validation, so it could be two type of things. One is basically your production testing. So production testing is good for your IO, AC timing characterization, and manufacturing test. And second is design testing, whether you have met the required design intent or not. So this is basically good for if whether it's a logic issue or bug or not. So two platform of validation. One is where you measure your IOAC timings, you characterize and do a manufacturing test whether there is any fault or not, you have shorts or not. Second, this is basically to find the intent, whether against your rules, what was the intent of your chip, whether that intent is working fine on silicon or not. So So these are the 4 targets of validation. You do, as we discussed, functional bugs, so whether functionally your chip is working fine or not. Second is your critical electrical issue hunting, whether is there any shorts or not. Is suppose during manufacturing, is there any issue, your 2 metals get shorted. So all these things would be caught in your circuit or electrical issues. Then you also do analog characterization. So this is like an eye diagram. So ultimately, suppose you have a high-speed DDR interface. So you boot up your chip. You are trying to read and write from an external memory through on a DDR interface, but whether you are getting a right waveform or not. So all those analog characterizations are part of your validation, and then you are also doing a benchmarking and internetworking, whether your basically how overall. Okay, so when you manufacture a chip, it would be with a different processes. All dies will not have the same RNCs. So if some dies would we call, let's say, worst case die, some call it the best case die. So we will measure we do a throughput comparison that how the overall we are doing against the benchmarks. So this is all regarding the overall SoC design flow. So we covered both the front-end part and the back-end part. So we are doing we have seen a lot of advancement in the last 20-30 years. But this SoC design flow, this will continue to be the recipe for the design effectiveness and efficiency. They are the standard practices which every design company need to follow to finally design a chip. So it is so this process is required to support the industry value chain for the product development. And this is still a very hot field. There are the vast opportunities for the career development. There are the specialized roles, as we discussed, PDK, custom cell development, SoC development, DFT, verification, test engineering. So all these are very niche areas, and they are the specialized roles, and where you can expect to do a cutting edge work, and you have a specialized expertise area. So everyone cannot be master of everything. And so you have design thing, but then you have automation, like you have the area tools, which will provide you the tools to do this design. And as Gaurav covered, that the safety, security, and reliability are going to be even more important in the coming times. So all they are the vast overall opportunities for the career development in the semiconductor design. So these are some of these things that we should focus on the overall skill development to make best use of the concurrent opportunities. So fundamentals are always important. The analogs, digital microprocessor, whatever you learn in college. So you will find some application of that, and you will once you start into your VLSI field, you would even relate more that why those concepts were taught. So even the 8086 microprocessor we learn in the college is still relevant. The concepts remain same. Yes, your microprocessor have become more complex, but yes, the fundamental concepts like virtual memory and all those things remain same. Then area tools, so scripting and all those things are also very important, because so there is a big area industry. So the companies like Cadence, Synopsys, which are developing these tools to help in the overall design thing. So I am still excited after 16-17 years. So I think it's still the very good time to be a young engineer in semiconductor design. And Gaurav, your thoughts on this?
Thank you, Paul. I think you summarized pretty well, right? It's like after 17 years, like it is like go to learn, right? Still education. So I'm particularly looking at the education domain last 17 years. But yeah, so all these topics that we discussed today, so although you we just covered them on 1 or 2 slides each topic, but they are very vast, right? So it's like kind of a research topic itself, where many people spend their whole career, right, on one particular function, or maybe just couple of functions, right?